Hi everyone. Hope you're all doing very well. This is the last stretch before the Christmas vacation, so thanks for being with us. This is our last seminar for 2023. We will start again on January 22nd. The first two seminars of 2024 will be presenting the results of the 5 Climax starting grants. So stay with us for these two seminars in 2024. But before then, and today, we have a very interesting presentation from Professor Wendy Queen and Professor Kumar Agrawal. Thank you for being with us today. The seminar will be in English, but feel free to ask questions in French, and I'm happy to translate as needed. The two experts today were asked to prepare a presentation of about 20 minutes, and each will be followed by a Q&A on their presentation. You can also find all of the previous seminars on our YouTube channel, so make sure to check it out if you missed interesting topics to you. So we'll start with Professor Wendy Queen. Thanks for being with us. Let me introduce you. Wendy Queen completed a PhD in chemistry from Clemson University in 2009. She received a fellowship to study neutron scattering at the NIST Center for Neutron Research from 2009 to 2012. She was then appointed a project scientist at the Molecular Foundry at Lawrence Berkeley National Laboratory from 2012 to 2015, and then appointed assistant professor at the Institute of Chemical Sciences and Engineering of EPFL in 2015. She was promoted to associate professor in 2022. Her research focuses on the synthesis and characterization of novel porous adsorbents that are of interest in a number of gas and liquid separations. Thank you, Wendy, for being with us. You can share your screen and the microphone is yours.
I just want to say before I get started, thanks to Climax for the invitation to be here and speak. Also today, I'm gonna talk to you about some of the work ongoing in our lab. So we're interested in designing highly porous adsorbent materials. Today, I'm specifically going to tell you about one very important separation that we're working on, and that is the separation of CO2 from dilute gas mixtures. So our group, we specialize in separations, and the reason that we're specifically interested in those is because currently the world is expending between 10 and 15% on separations alone. This includes both gas and liquid separations. Now, this number is already huge without the large-scale implementation of carbon capture efforts. And so really the goals of our group are to design materials so that we can specifically begin to help reduce the energy input into existing separations, or design materials so that we can begin making separations that are deemed impossible now possible. And so there are many different separations that can positively impact our planet. I show you 8 here. However, there are many more. The first 4 shown in red are the ones that we are predominantly working in. The first is the separation of greenhouse gases from dilute gas streams, specifically small molecules like CO2. Of course, we're interested in separating these and capturing those because they're implicated in global warming. The second separation is the removal of trace contaminants from water. This is, of course, very important because clean water is required to sustain human life. We also know that with continued climate change, we're going to have less and less access to clean potable water. The third separation is the separation of rare metals, not just from ore, but also from waste. This is very important because we need a lot of critical metals and minerals, basically, for all of these clean energy technologies that we would like to implement. So it's really important that we improve the separation processes from ore, but also make this process more circular by recycling those from waste. And last, but certainly not least, we're working on oxygen separation from air. This is, of course, important for several reasons. Currently, it's done using distillation, which is super energy intensive. but it's important for instance, patient therapy, for medical oxygen concentrators, for instance. Also, of course, for oxy-fuel combustion-based technologies. And there are a number of other important separations. I give you a few more examples. There's supposedly enough uranium in the sea to supply the world with energy, but of course, the sea is a very complex matrix, so currently the separation is not done on large scales. Also, the separation of hydrocarbons is extremely important, not just for power production, but also we use these to make a lot of other fine and commodity chemicals, for instance, like plastics and pharmaceuticals. So there are a number of different separations, but I think one of the most important separations of our time is related to the separation of CO2 from gas mixtures. And if you look at the number of global energy-related CO2 emissions, it's around 36.8 gigatons per year. This is for 2022. About 22% came from the transport industry, which is a difficult emission to effectively capture because it's kind of sparse. Also, you have CO2 emissions coming, for instance, from large-scale power plants that are producing the electricity needed, for instance, for us to heat and cool our homes. This is on the order of 40%. And so because of these large-scale emissions, we're interested in designing materials for their separation, for instance, from post-combustion flue gas that might occur at a plant that's using, for instance, natural gas or coal, for instance. They mix that with air, combust it, and then on the back end, what you get is a mixture of gases. It's about 15% CO2. Actually, it can range between 5 and 20%. But it's predominantly nitrogen. There are other impurities and small trace, small molecules in there like SOx and NOx, oxygen. Of course, these streams are also very humid. So in addition to post-combustion capture, our materials can be extended to other separations. Importantly, there are some difficult to abate emissions in the future that we need to take care of. CO2 coming from cement and steel industry, as well as incineration facilities. And we're also interested in designing materials for direct capture from air, which is, of course, extremely important if we want to reach net zero and even go negative and get those past emissions, so to speak. So if we look at post-combustion capture, the most mature capture technology is related to liquid amine scrubbers. Now, these are really fantastic materials. They can absorb a lot of CO2 and they can do it selectively. The problem with these materials is that they bond CO2 very strongly. They're also highly diluted with water, which means they have very high heat capacities. And as a result, in order to release that captured CO2, it requires a lot of energy input. And so here, effectively, if you implement this technology to power plant, you can expect to decrease the efficiency of that power plant, for instance, by 30%. So the idea is that people are exploring other technologies. You'll see one today from Kumar related to membranes. Our group is focused on the design of porous solids, and the reason is because solids naturally have lower heat capacities, which allow them to be a bit more energy efficient. And you could cut, for instance, that parasitic energy loss by at least a factor of 2. So today I'm going to tell you about a number of different porous materials. The first being metal organic frameworks. We're really interested in these materials because they are highly tunable. They also have, because of this tunability, they also have very high CO2 capacities. Other materials that we're working on, effectively, we're learning how to pyrolyze, for instance, these metal organic frameworks and other porous coordination polymers so that we can produce, for instance, activated carbons. Now, traditionally, activated carbons have kind of suffered from low CO2 capacity and low tunability, but we are specifically trying to learn how to modify these materials in order to enhance their performance. And so these are the 2 classes of materials that I'm going to show you today. I doubt many of you are familiar with metal organic frameworks. So these materials are classically defined as consisting of metal ions or metal ion clusters that are linked by rigid organics. You can see the metal ions here in pink, then the organics in gray. Now, this is just a cartoon. You would effectively mix these 2 building blocks in solution. They come together and they form these really beautiful porous crystalline materials. Now, if you notice, most of that material is basically open space, okay? So this means you can put a lot of guest molecules inside. So if we take a look at a real MOF, so this is the prototypical MOF referred to as MOF5, here you can see these metal ion clusters with zinc ions in blue interlinked by these rigid organic linear units shown here. Now, these materials are really interesting because you can easily change the building blocks that you have, the metals or the ligands. And as a result, tens of thousands of these materials have been synthesized to date. So we can engineer materials with various pore sizes, with channels that propagate in 1, 2, and 3 dimensions. As you know, the walls of these materials literally are atoms thick, and this gives rise to world record surface areas. So in a single gram of material, you can have surface areas as high as 7,800 square meters. Also, pore volumes above 5 cc's per gram, for instance. This allows us to effectively put a lot of guest species inside. As mentioned, they're highly tunable, and this is interesting. For instance, you can go from this linear link now to this trigonal link to allow you to tune the pore shape and the pore size. You can imagine you could also elongate these links to tune the pore size. In addition, you can functionalize the surface of your organics, and this will allow you to kind of tune how your material interacts with incoming guest species. And for instance, boost both our capacities, how much we can absorb, and how selective our materials actually are. So from there, our goal is really to design materials that when we have a gas mixture can grab that CO2 and allow the other small molecules to pass through the material. So our goals initially really are to design a material with a relatively high CO2 capacity, so it absorbs a lot. It's selective for CO2, particularly over nitrogen, which is the main component in post-combustion flue gas. We want a material that can not only absorb CO2, but also release that CO2. And we want it to do this over a long, extended period of time. And the reason that we want that, of course, is because we don't want to have to replace our adsorbent every few months. Of course, we would also like to have a moderate regeneration energy because this basically reduces that energy input that's required for our entire process. So from there are 2 different types of materials that I'll show you today. The first are MOFs that we're modifying with amines. These are chemisorbents. So the amine has a physical or a chemical interaction with the CO2, forms a covalent bond. This means that these materials absorb the CO2 really strongly. We're also looking at the other end of the spectrum with these nitrogen-based carbons, which are actual physisorbents. This means that the type of interaction they have is not a chemical one, it's a physical one. So it's electrostatic in nature. And so we're trying to learn how to enhance the amount of CO2 that these carbons can absorb at low partial pressures. And so here is the first material. So we're learning how to decorate MOFs with amines. So what we do is we make our MOF. Here is our ligand, and you can see it's got an amine functionality. We then modify that with this bromoacetyl bromide, and this forms a bridge. And we can use this bridge then to covalently graft a variety of other amines, like the ones that you see here, like this ethylene diamine. We can increase the number of primary amines all the way up to polyethylene amine, for instance. So here, basically what we've made is a MOF that's now modified with loads of different amines inside the material's pores. So let's take a look and see what it does to the CO2 adsorption properties. So here in black, you can see the parent MOF. You can see here in this low pressure regime, this is the approximate partial pressure of CO2 in post-combustion flue gas. When we modify it with our first amine, we see a slight increase in capacity. And then you can see that as we modify it with more and more primary amines, we see significant improvements up to about 1.5 millimoles per gram for this material. Now let's look at what it does to the nitrogen. Here you can see that the amount of nitrogen, it's about 0.8 bar, which is the partial pressure of nitrogen in post-combustion flue gas. You can see that it actually absorbs very little nitrogen. As a result, this gives rise to high CO2 over nitrogen selectivities. So the parent material is less than 20, and you can see that when we modify this with various amines, particularly the polyethylene amine, we get to selectivities over 400. The reason is because we're enhancing the amount of CO2 it absorbs, but we're also decreasing at this same time the amount of nitrogen, for instance, that the material absorbs. So from there, we'll look at the isosteric heats of CO2 adsorption. This is simply the average binding energy at constant coverage. And so here, if we look at the parent MOF and then the material modified with ethylene diamine, what you'll note is that the binding energy is effectively very low. These are pretty much in the physisorption regime. Now, when we look at materials with high densities of primary amines, what we see is an increase in the binding energy up to the polyethylene amine. We can see that it goes up to about 90 kilojoules per mole, which is in the range of chemisorbents. So from there, what I've shown you is that we effectively assess these materials first in single components, so in pure CO2 or pure nitrogen, but now we need to see how it looks in an actual separation. So here, what we do is we put our adsorbent in a column, like the one you see here. Then we stream a gas mixture through that column. And so I told you the main components that we want to look at are CO2 and nitrogen, of course, in humidity. So what happens is that our adsorbent will adsorb the CO2. The nitrogen will pass through and we'll see it break through the column first, okay? When the CO2 breaks through, this means that our adsorbent is effectively saturated. And so here what you're seeing are the breakthrough curves associated with the MOF in dry and humid conditions. And what you'll note is that under dry conditions, the separation time for nitrogen and CO2 is about 10 minutes. Under humid conditions, that decreases significantly because the water is competing for the CO2 for bonding sites. As we add our amines, this is the first amine, ethylene diamine. You can see under dry conditions, we've already made an improvement. The breakthrough goes to 15 minutes. And then under humid conditions, it improves significantly. Again, as we increase the number of primary amines, we begin to see really large separations between nitrogen and CO2 under dry and humid conditions. TAEA has a dry separation of 61 minutes and then 74 minutes under humid conditions. And then finally, we see the PEI, which is our best performing material because we get the largest separation time between nitrogen and CO2, 70 minutes under dry conditions and then 90 minutes in humid conditions. And so from there, I told you that we wanted these materials to be cyclable. So we look at the adsorption of CO2 and we look at its release over many cycles. And so this is what you're seeing is a weight gain due to CO2 adsorption and then a weight loss due to its release. And so here you see our best two performing materials, the PEI and TAEA modified material. We do the adsorption at 40 degrees Celsius, and then we do the desorption at 120 degrees Celsius. So that's how we release the CO2. And here we've cycled the material over 200 times, and we see very good cyclability. We're not seeing significant losses in terms of our material's capacity. So from there, we've done some other modifications to try and further optimize the amount of CO2 that our materials can absorb. And so here I'm showing you again the bare MOF. We've made other amine modifications, and we've been able to get our adsorption capacity at about 0.15 bar up to around 2.2 millimoles per gram. Now, before I told you the previous adsorbent was about 1.5. Here you can see the binding energy associated with the parent MOF and then the amine modified materials. Here in this case, we're going up to about 125 kilojoules per mole in terms of the binding energy. And then if we look at the CO2 selectivities of these materials, we again get extremely high CO2 selectivities, which are well above 200 in this case. And so from there, I don't want to go through all of these, but I'll just show you the best performing material. In this case, you can see that we've now been able to improve the breakthrough time from the previous best, which was 90 minutes, up to about 142 minutes under humid conditions, which is really nice. So from there, we've looked at the cyclability of a material. I apologize for the fluctuations. This is due to thermal fluctuations in our laboratory, which are out of our control at the moment, but we're trying to get this fixed. But what I want to point to is that over 1,000 adsorption and desorption cycles, we see a very flat baseline. This is really important because if you see a decrease in your baseline, it's because your amines are leaching, so you're losing them. If you see an increase, it's typically because you have CO2 that is binding irreversibly, which means you're forming other species like linear or cyclic ureas. And so we don't see either of those things, which would imply that our material has very good cyclability over these 1,000 cycles. So from there, we're also exploring physisorbents, as I mentioned. And so one of the problems with carbons is that they typically have a very low CO2 absorption in the low pressure regime. Now, the really great thing about carbons is that they effectively are really super stable. And so if we could find a way to enhance these, their performance with regard to CO2 capture, then certainly we know that the adsorbent is going to have extreme longevity in terms of lifetime. So what we've done is we've taken a MOF. We simply put this small molecule, which is a bromophenanthroline, inside the MOF, and then we pyrolyzed it. So this is how you produce carbons. What happens is during the pyrolysis process, this small molecule cross-links to form polymers inside the pores, and this is driven by the cobalt, which is the building unit in the MOF. And so then after we make the carbon, we treat it with an acid, we release the cobalt, and we can reuse that, for instance, for MOF synthesis. But what we're left with on the back end is a highly porous carbon. It has a surface area of almost 600 meters squared per gram. And it has a very high density of micropores, so well below 2 nanometers is the pore size, but also a very high nitrogen content, which comes from both the MOF as well as the polymer that we've put inside. And so what we find is that this significantly enhances the CO2 adsorption properties. So here, I'm just showing you the MOF, the parent MOF in black. You see it's got a very low CO2 adsorption. We carbonize that MOF. It's still got a very low CO2 adsorption. And then we treat it with acid to leach the metals out. Still, again, the CO2 adsorption is not adequate. However, when we functionalized it with this bromophenanthroline, which helps form this high density of micropockets in the material, we see significant improvements in the material, particularly after we remove the cobalt, which frees up these really nice micropockets for the nitrogen or the CO2 to bind in. And so we see really nice capacities for these carbons. It's about double what we've been able to find for any commercial carbons on the market. And so here you can see the isosteric heat, which is the average binding energy at constant coverage. Note that it's just above 35 kilojoules per mole, which again is implying that it's in the physisorption based regime. So it's not binding CO2 super strong. And so from there, we've looked at the breakthrough measurements of the material. Here you can see the nitrogen breakthrough and then the CO2 breakthrough under both dry and humid conditions. And the separation times range from 33 to 40 minutes per gram of material. Now, this is not nearly as high as our amine-based materials. However, we know that with these materials, our cyclability is likely to be much better, hence the reason that we're interested. Here you can see very strong cyclability with no decline, of course, in materials capacity. So from there, we've made several interesting physisorbents and chemisorbents that we would like to now implement into an actual separation process. However, we've got a small problem. When we make these materials, we're making them as very fine powders, and these are very difficult to handle on large scales, but also when we implement those into an actual separation, it creates a large pressure drop across our column, which is not good. So basically what we have to do then is take these fine powders and structure these into tablets. To do that, we're basically using a die like this and a hand press. And then we make these tablets. We're basically developing different protocols. And then we test how mechanically stable the pellets are. And once we have a pellet basically that has similar performance to that of the parent powder and also is very robust, then we can transfer this into this automated tableting machine, which can actually make around 2,000 tablets per hour. So from there, this is what we're doing. We're scaling our materials up and we're structuring those specifically so that we can implement those into a small scale pilot plant that we've built here at EPFL. Up front, we have a gas mixing system. So you can make gas mixtures, for instance, that contain nitrogen, CO2, and water. You can also put other impurities in there like SOx and NOx. We can also handle industrial-based gases in this system. You'll notice here we've got 3 different adsorption columns. These columns are about 1.2 meters in length, which means that they can handle kilograms of material. Also, because we have multiple columns, when one is adsorbing, we can be desorbing in another, which can allow us to get at least a semi-continuous process going. We've got on the back end an analysis system, which just consists of a mass spec that can tell us what is coming through our columns, which gives us an indication, for instance, when our adsorbent is saturated. We've also got a compression system on this pilot plant so that we can compress the CO2 and store what we have separated, or we can pass that downstream, for instance, to one of our colleagues who has a methanation process going on the back end. And so these are just some specs associated with our unit. One thing that I didn't mention is that this unit, I've shown you only temperature swing based processes where you're changing the temperature during the adsorption and desorption for releasing the CO2. This unit can do temperature swing. It can also do vacuum swing or pressure swing. Also, it is fully automated, so it can run free of human intervention for weeks or months on end if needed. So from there, what we aim to get out of this project is effectively key performance indicators. And so we want to be able to determine the CO2 purity, the CO2 recovery, productivity, things like that, not just for each material, but also with varying process parameters. And what this is going to let us know on the back end is effectively what is the economic and energy cost of the capture process. And so from there, this is just a look at our pilot plant that has been constructed. So it was already built, and also the factory testing is done. It's at EPFL now, but we're waiting for its installation. Well, we're waiting for the building to be finalized so that it can be installed. And so our goal with this unit is not only to demonstrate kilogram scale capture, we're going to be benchmarking our adsorbents against other commercial-based adsorbents to compare their performance. But our real goal on the back end is to identify the best material and process parameters that effectively lead to the lowest energy and economic costs for the capture process on the back end. And so from there, now on to the summary. So where we are and where we're going. So I've shown you that we've been able to successfully design a number of novel chemi and physisorbents that can indeed separate CO2 from gas mixtures. We have shown that they demonstrate high cyclable capacity in humid CO2 and nitrogen mixtures to date. Now we're aiming to scale up and structure these materials in the lab. We normally work with milligram scales. And so we've gotten it up to gram scales, and now we're going kilogram scales. And the only limitation here, of course, is the size of our reactor. We're waiting to order a new 10-liter reactor, which I believe will put us from the 20-gram scale up to the 200-gram scale in terms of synthesis. So we have already built the small scale pilot plant. It's designed and factory tested. And then next year, we're aiming to implement our adsorbents into this pilot plant and begin benchmarking those against commercial adsorbents. And of course, determine all of these KPIs, which is going to allow us to optimize the process and materials input for the capture process. And so beyond, Kumar will probably talk about this. It's a solution for a sustainability project where large scale capture will be carried out on the ton scale at an incineration facility in Valais. And then we're also going to have a kilogram scale demonstrator for direct air capture as well. So with that, I have to thank my wonderful team of people. They're responsible for all of the amazing results that we've gotten for CO2 capture in the last few years. Of course, the funding agencies, you for your attention, and I'm happy to take any questions that you might have.
Professor Kumar is a chemical engineer from IIT Bombay. He received his PhD from the University of Minnesota, developing zeolite membranes for energy-efficient separations of petrochemicals. He got his postdoctoral training at MIT on ice formation in carbon nanotubes at room temperature. At EPFL, he's developing membranes for low-cost carbon capture and is leading EPFL solution for sustainability project for large-scale CCUS demonstrator. Thank you for being with us today, Kumar. The microphone is yours.
Thank you, Nicola. I'm Nicholas. I'm trying to see if I can share my screen successfully. Thank you for giving me this opportunity to explain the work that we have been doing, which is close to one of the goals that Climate has. And so really appreciate the audience here. So overall, what I can summarize is we are doing work on developing a technology which is based on membrane-based separation technology. What is this separation technology? Is essentially it's a filtration, if you can think of that at the molecular scale, where you're removing CO2 from nitrogen based on the affinity of these molecules to filter through a material that we have made as a filter. Right. So in this presentation, I will talk about our filter, which is made of atom thick film of graphene. So it's actually the filter is atom thick. So it's the thinnest possible filter. And the filter that we have designed is very effective in terms of filtering out CO2 from nitrogen. On the right, you are seeing a picture of one such a filter that we have been able to scale up recently to about an A4 sheet size. And these are being tested now at some of the kilogram scale demonstrator that we have. Now, this was quite apparent from Professor Queen's presentation, why we are focusing on the field of separation, because if you look at any traditional chemical industry, about half of the energy in that industry is consumed by separations. So, of course, increasing the energy efficiency of that separations, especially if this is carbon capture, is going to be very relevant. And why carbon capture is sort of very evident if you look at the plot of how the temperature of our climate is linked with respect to the amount of CO2 that we have emitted since the Industrial Revolution. There is a direct correlation, and we have a limited budget in terms of what we can do in terms of releasing CO2 to prevent it to go beyond 1.5 or 2 degrees C scenario. And all of this is very relevant because carbon capture is separations. It's also from a point source that I'm going to talk about today, but also if you think of direct air capture, which is negative emission, it's also separations. All right. So there are ways to do carbon capture from various streams of the industry. One is post-combustion carbon capture that Professor Queen just showed. Essentially, it is done at pretty large scale in the chemical industry, typically millions of tons of CO2 by Shell, for example, in Canada, where essentially they take a flue gas and the flue gas is treated to a liquid amine. And this liquid amine then absorbs CO2 quite efficiently. Now, the issue with this method is that once the liquid amine is consumed, you cannot just throw it or store it because these are expensive and you have to do a continuous separation. So you have to regenerate this liquid amine by heating it. And it's that thermal energy process for amines that becomes really prohibitive for doing this separation wide scale for many other industries. The other source for CO2 is also during hydrogen production. So a lot of us we hear about hydrogen economy, where we are going to do a lot of things with hydrogen. But if you look currently how hydrogen is produced, over 95% of this is produced by steam reforming of fossil fuels. So, and there you have to separate hydrogen from CO2. This is again currently done by solvents. And then there is also an oxy-combustion capture, where the idea is instead of burning everything in air, we can burn everything in oxygen to make a pure CO2 component. But for that, you have to separate oxygen from nitrogen. Now, we are working in the field of membranes, mainly because if I look at all of these processes that I mentioned here, they're all using thermal energy. And generally, it is very well accepted that as long as CO2 concentration is not too small, we are not talking of CO2 from atmosphere, then we can use membrane-based process, which is not dependent on thermal energy, but dependent on electrical energy. And the driving force is concentration difference across the membrane. Then the energy that you need for capturing carbon becomes less. Right. So that is essentially a bit of background I wanted to give on the separation process. Now, what we are doing in our lab is, of course, trying to make another unique kind of a membrane. What is the uniqueness of this membrane? One, it is a membrane that has a selective layer thickness of just one atom. And this is essentially motivated by the fact is a thin film would give you the highest possible flux. And that is very important because if you have a thin film and you have a high flux, then you need only a small membrane area, and that would reduce to a lower capital cost. Right. So therefore, these membranes can be very attractive when you want to have a small footprint of your process, right? Where footprint is important. The way these membranes work is essentially we'll take a graphene sheet. Graphene is a sort of a allotrope of carbon. Essentially, when you write with your pencil, you're making a graphene. But graphene itself is not a filter. Graphene is very dense. In fact, nothing goes through graphene. So what we do is we make tiny holes in graphene. These holes are of the size of the molecule that we want to separate. I'll give you a sort of description of a size in the next slide. But the idea is once the hole size is comparable to the size of the molecule, when the molecule now goes and interact with the hole, or it wants to go across the hole, it feels the interaction from the edge of the pore. And that interaction is then accounted as an energy barrier to transport the pore, to cross over the pore, right? And so the larger the molecule, larger the energy barrier, and this energy barrier is related to the flux of the gas through you can say transition state theory. And therefore, essentially, this energy barrier, larger energy barrier, leads to much lower flux. And so based on this energy barrier, you can have selectivity between gas molecules. All right. So if we can design holes for CO2, where the size of the holes are similar to that of CO2, we can then have selectivity from graphene membranes. And because it's just one hole and just one atom thick, we can have quite fast transport. And the very attractive thing for chemists or chemical engineers at EPFL, as we are, to think is that once we can do this, we can target many other separations, right? Because we can change the size of the hole, we can target different probe molecules. So then the chemistry challenge for us when we started the project was, of course, graphene doesn't have any hole. How do we create such holes? So essentially looking into chemistry of that. And not just any hole, right? The holes have to be of a particular size and will have to have but a few characteristics. So here I define 3 different characteristics. First challenge is that you have to have the hole of the size of the gases. Now, how big are the gases? So here are some of the light gases. So CO2 is here, 3.3 angstrom. The other gas that we want to separate is nitrogen. That's the predominant gas in your flue gas, right? So the size of CO2 is 3.3, nitrogen is 3.64. So you have to prepare a pore which is angstrom size, but is not bigger than 3.64 angstrom. All right, because if you have a bigger pore, they will allow nitrogen to go through. But what happens with bigger pore, there is no barrier, as I mentioned in the previous slide. So the molecules go really fast. And so one big pore will destroy the selectivity that you get from about 2,000 pores. So that's a big challenge. So we have to be very specific in making a tight control on the pore size distribution. And the second is we have to not just make one pore, but we have to make ensemble of pore. And so we have to have a certain pore density. So the process that we have to do has to be very uniform and should be easily be applicable. So the first proof of principle, so this field is not that old, so the first proof of principle in this was about 10 years back. This is not my group, but a group in US, where they essentially looked at a simple 5 micron size graphene coupon. This was suspended on a pit, and they were doing AFM by pressurizing this with a gas. And by making a hole, by oxidizing it, they were using ozone in combination with UV, where you make this atomic oxygen. They were able to oxidize it. And they showed at that time that once graphene is oxidized, it can pass small molecules like hydrogen and CO2. You can read the molecular size on the x-axis much faster. So on the y-axis is the leak rate of these molecules, much faster than the bigger molecule like nitrogen and methane. So this was the proof of principle. And this was from my 5 micron size pores, but this proof of principle stayed until 2018, because at that time, nobody could actually make devices of atom thick membranes without any cracks or tears. And it was also very difficult to reproduce these chemistry experiments. And one of the challenges in reproducing this chemistry experiment was also a fundamental challenge in chemistry, which is how do the oxidation of graphene or graphite takes place? So there have been many attempts in the past trying to look at studies of oxidation of graphite. What has been shown is that when graphite is oxidized, we get these linear looking cracks that we can see in optical microscope. We can make graphene oxide, which is a very popular material now. And in graphene oxide, what people started to see is that there is a phase separation of material itself, in a sense that there is a hydrophilic oxygen domains, and there is a hydrophobic pristine domains. And what has been also shown is that once you heat this material, you release CO2 and then you incorporate porosity. But the exact precision of how this chemistry happens, how to control it, because remember, for gas separation, you need to have a precise pore size distribution in graphene. So this is what we were chasing. And so without going into a lot of other detail, I will just quickly summarize this here. So what we showed was that when graphene is exposed to oxygen or a reactive oxygen, in this case, we were using ozone, first, what you form is an epoxy group. So essentially, it goes through a sort of an energy barrier. So this is essentially the thermodynamics of the reaction. You have to spend about 70 kilojoules per mole of energy to make this single epoxy graft onto the graphene. All right. And then there's something very interesting happens, right? So usually you would think that when you are making an oxidized material, it will be very amorphous, it will have no order. But what we started realizing through time that indeed we were very lucky that there is an order in these oxygen groups. So they would essentially organize themselves nicely in a predictable orientation, and they will make dimers, trimer, and then they will make a trimer chain. And these chains are essentially running linear. We could see them by our scanning tunneling microscopies. What you are seeing is an oxygen chain running on graphene. And these chains would then organize. If you increase the density or if you continue the reaction, they will make a bigger cluster. So you can now see a bigger clusters. And if you provide energy to these clusters, then the central part of this cluster, which is much more reactive, will gasify, leaving a hole. So this became a very interesting technique for us because we could prepare all of this from this step to this step in a very uniform way without preparing a hole, and then we can decide when to open the hole. Just to show you how the hole forms, so this is an experiment we did in transmission electron microscope. So in the microscope, you can suspend the graphene, and you can oxidize all the way till this step where you have not necessarily formed a hole, and then you can expose it to the electron beam. And once we do that, we see a hole forming at the center of this cluster. And we can look at the size of that hole as a function of the dose that we see, right? So we see there is a sort of a linear correlation between the size of the hole and the dose. And so this says the size of the pore can be controlled by the amount of energy that we give. So that was a very interesting study for us. It also allowed us to estimate the amount of energy we need to spend to make these holes. And this allows us to essentially design our experiment very well. So in a nutshell, if I summarize what I've said so far is I talked about two different energy to create the first atom here and the energy to create the hole. The energy to create the first atom was about 70 kilojoules per mole. Energy to create the holes is about 130 kilojoules per mole, right? So you can see the energy to create hole is much more larger than the energy to create the atom. So we said, now we can decouple this to reaction. And this realization allowed us to make the whole process very simple, right? So essentially what we do is we start with graphene, and nowadays you can purchase commercial graphene at meter scale. It's not a problem. And then you can expose this to an oxidant. In our case, the oxidant is ozone. Why ozone? Because if you want to do this on a larger scale, ozone can be conveniently used. We can do this near room temperature. Ozone is very reactive towards graphene. 70 kilojoules per mole, the number that I talked about, is very accessible at room temperature. And then you make a graphene oxide kind of a structure on a single layer. All right. But at this stage, there are no holes, right? So, and once we provide energy to this, this can be, for example, heating. Then you can create holes, and depending on the amount of heat you give, you can tune the size of your hole. Just to give you an example of tuning the size, so or just adjusting the pore size by heating, this particular coupon of graphene, porous graphene, was made by heating at 100 degrees C. And what we are doing is we are looking at which gases come across graphene. So what we saw is the helium coming up the fastest, followed by hydrogen, CO2, nitrogen, and methane. This is along the expected size, the size of the gas molecule. Helium is the smallest, so it comes fastest, then hydrogen and CO2. So this is a true filtering effect where the smaller molecule is coming faster. All right, so then we can increase the size of the hole by heating it to higher and higher temperature. So this is heating this to 120, 150, and 200 degrees C. And what we can see is that now CO2 starts to come faster as well, because now the hole size has expanded. So the energy barrier for CO2 to cross the pore is less, and so it can permeate faster. And we can control it in a way that nitrogen doesn't go through, so you can get CO2 nitrogen selectivity. All right. This is just for to show that we can do this in many different ways. So what I was showing before was by heating. We realized we can also do this by exposing graphene to those clusters to simple light. So this is a 390 nanometer light. So this is near ultraviolet, violet color light. And if you just expose those to a few 5 seconds of time of this light, we start to form these holes. Right. So here are some of the pictures of how these holes look like. So these are aberration corrected transmission electron microscopy images. And what you're seeing is really the atoms of graphene organized in a honeycomb lattice, and in between we have removed the atoms by gasification or by oxidation. And so these are the different pores that we form. And once we look at an ensemble of these holes, what we see is what we have is essentially a pore size distribution. Pores characterized by a number of missing carbon atoms. And what we see is that most of these pores are permeable to hydrogen and CO2, and very few pores are permeable to nitrogen and methane. All right, so as a result, we can further optimize this process. So we have over a course of time, we have developed a lot of different chemistries and a lot of different ways of making these membranes. And so I've sort of now go more towards application side of these. And so we have done a techno-economic analysis where we have looked at performance and membrane cost, separations cost of preparing these membranes. And what I have here is different generations of the membrane that were prepared in our lab. So the green one is the first generation, second generation, third generation, and this is the latest generation that we have in the lab. And essentially what we have been able to show is that by changing the porosity, by optimizing the pore size distribution, and by also functionalizing these pores with nitrogen, you could see that, you saw that in Professor Queen's presentation, that using nitrogen atoms in carbon can help to improve the selectivity. So we do the same thing also on the atom thick film. We were able to improve our performance, which is expressed in terms of selectivity and permeance. And once we do that, we could sort of say, if we scale up these membranes to a large area membranes, the capture penalty of CO2 can be quite attractive. So already in 2019, which is our first generation membrane, these were about $30 to $40 per ton of CO2. That's the capture penalty, and this is about now we are below $30 per ton. And why these numbers are important? Because, for example, if you look in the context of Switzerland, currently the CO2 levy is about $120 per ton of CO2. So this is already much lower, which would make the industries very much attracted to try and use a separation technology, which has a lower cost than the CO2 levy. All right, so how does the separation process takes place? So essentially what we have is we take a feed. Let's say this is a feed from combined heat and power or even coal-based power plants. So we don't use coal-based power plants here in Switzerland, but for example, in Europe or China or India, this is US, China, and India. This is pretty prevalent. And then what we can do is the flue gas is coming at 1 bar. It can be compressed to a higher pressure, so 2 bar. And on the other side of the membrane, which we call as permeate size, we can use a vacuum pump to pull a moderate vacuum. And with this already we can see that we can go from 13.5% to about 50%. So we have gone half the way in purifying this. And then we can do a second stage where we don't have to pressurize anymore. But on the permeate size, we pull a sort of a weak vacuum, about 0.2 bar, and then we can recycle. And by this way, we can get up to 95% purity of CO2. And our latest optimization with these kind of membranes has shown us that while the commercial process, which is based on liquid amine, consumes down to 3 gigajoule per ton of CO2 with capture penalty and different concentrations of CO2 ranging from $50 to $110 per ton, we can reduce it by a factor of 2 to 3, so less than 1 gigajoule per ton of CO2, and $20 to $30 per ton of CO2 for capture penalty. Of course, these membranes that we are developing at EPFL are much better in terms of the gas permeance for many industrial and all of the state-of-the-art work that has been shown. The selectivity that we show here is about 50, which is already quite good to design a membrane process to achieve a purity of 95%. And so if you take this kind of a membrane and look at what is the specific energy and specific area and capture penalty with respect to all other state-of-the-art membrane technology, we can show that this becomes really attractive. And in particular, the specific area, which is essentially the footprint of this membrane, can be quite low compared to what is out there. So which makes it very attractive, especially when the footprint is a challenge. All right, so all of these calculations are, of course, assuming we can achieve a large scale, right? So while we are doing chemistry, we are also very interesting to make sure that we can ultimately scale these membranes to a size where they become interesting. And that's a non-trivial challenge, because essentially what we are working here is atom thick films, which tend to break down very easily. So in 2018, we provided the first proof of principle of a working membrane, which is more than a micrometer scale, right? So this was by making sure the graphene doesn't break, and we came up with an out-of-box idea. This out-of-box idea is so essentially taking graphene and reinforcing it with a support that the support doesn't break, right? So usually people in the field of membrane, people put the selective layer on top of a support. Here we were putting support on top of the selective layer, and that essentially allowed us to prepare these membranes without having them break. And since then, we have been successfully able to make centimeter scale membrane. And about 2 or 3 years back, 2 years back, we had the project from Valais administration in Canton of Valais, and with the help of Gaznat, we had this project to set up a demonstrator for a kilogram scale CO2 capture. And the idea was to get down to a meter scale, and then we envisioned to make these a much larger A4 sheet side coupon, which can be stacked. And very happy to say that we have achieved that now. And the demonstrator of this capture technology that we have developed is aiming at up to 10 kilograms CO2 per day, where you could see the membrane area that we need is not a lot, right? It's only 0.4 meters square because it has such high permeance. And this demonstration is now active in Agrawal. We have installed the membrane process that you see here on the right, and we are starting to test the graphene membrane in this demonstrator. This demonstrator is in Agrawal. We'll be very happy to talk more about it if you have questions. At EPFL, we also have a very nice project that started a few months back. It's called Solutions for Sustainability. And the idea is, according to the concept, that slowly we want to reduce the EPFL carbon footprint. And we want to reduce in fact, the energy-related carbon footprint of EPFL to about half by 2030. And one way to do that is to capture CO2 that comes from heating EPFL, right? So this is a sort of a example of that. I am in EPFL Valais, and this particular building is going to be heated through a waste incineration plant. This is in Ouvrière, an industry called NAV. Right, so this waste incineration plant will provide district heating, which will heat the building, and the emission for doing that is about 1 ton per day of CO2. So this project aims at capturing the CO2 that comes out of this plant at the rate of 1 ton CO2 per day. And if we are able to do this, then we are going to reduce the CO2 footprint of this building to 0. Of course, the idea is to capture, and then once you capture CO2, it will be stored in the liquefied form. And then we have collaborators in this project where they will take the CO2, they will make hydrogen from renewable electricity, and they will then convert that CO2 into a methanator with a very high energy efficiency of about greater than 70%. We also have a small project where we will look at converting the CO2 into a more value-added chemical, such as ethylene, which has much higher value compared to methane. Together with Professor Queen, we are also looking at capturing CO2 from air. These two projects are at kilogram scale, where methanation is also at ton scale. And this project has started now, and this will run for the next 6 years. So we now, under this project, we want to do a roll-to-roll production of graphene membrane, which is needed. And we're very happy to say that we are on the path of a startup. because we find the performance of this technology quite attractive. And so there is a lot of commercial interest in developing these technology so that they can be implemented at the low capture cost, right? So this startup is called Divya. You can find some information online if you search about this. So I'm going to skip this slide and directly come to my conclusion. And hopefully I could convey this idea that next generation membranes, what do I mean by next generation? So these kind of materials which have not realized before, they will simplify carbon capture because they simply have much higher performance compared to conventional membranes. And this performance is essentially because of the angstrom scale pores that we have incorporated in this material by exploiting the organization of oxygen. If you remember what we talked about, the linear chains and how these linear chain organize to form these pores. CO2 flux is very high from these windows because these windows are just 1 atom thick. And an actual demonstration with the actual flue gas from combined heat and power is ongoing in EGLE. And we're looking for very rapid progress in scale up. So meter square to tens of meters square to hundreds of meters square in next 1 to 2 years. With this, I'd like to thank the group, as of course, nothing would get done by myself alone. So these are all the students and postdoc who contribute and do most of the real work. And of course, my collaborator, which helped us to solve some of the hard problem in understanding the structure of the material, also computation and so on. And special thanks to the funding agency, especially Gaznat, which has really been with the project since the start of the project in our lab. They also sponsor my chair. I'm a Gaznat chair of advanced operations, but also the funding agency, including Canton of LA and SFOE. So that's all. Look forward for the questions.